this session, which is from Clement Delcamp.
Thank you very much, and thank you to the organizers for putting together this next workshop. So I'm not sure if what I'm going to talk about today really qualifies as a new direction in topological phases, because I will be talking about conventional topological order in 3 dimensions and their extended excitations. That being said, a lot of the results I'm going to present rely implicitly on some ideas of defect TQFTs, and these are very much relevant for fractonic topological phases. So it's not completely unrelated. So a familiar statement is the fact that in 3 dimensions, point-like particles are bosons or fermions. We don't have point-like anyons in 3D. However, we know that 3-dimensional topological phases host extended quasi-particles that have exotic or anionic statistics. And so in a way, we have a notion of extended anyons in higher dimensions. Now, ongoing efforts to better understand the kind of mathematical structures that classify topological phases in higher dimensions has led us to make a distinction between the notion of loop-like excitation and the notion of string-like excitation. And so one of my goals today is to clarify what I mean by this distinction. And roughly speaking, the idea is that the string-like excitations are more fundamental in the sense that several of those can be put together in order to build a loop-like one. And so I'm going to explain this process, at least at some level, focusing on a special class of models known as gauge models of topological phases, which can be thought as Hamiltonian realizations of the digraph return theory. And this is work I've been doing in collaboration with Alex Clement. So first, let me review briefly the 2D story. So generally speaking, we can define an excitation as some region of the manifold for which the energy is higher than that of the ground state. And we can, in order to characterize these excitations, we can exploit the following idea, namely that the properties of an excitation are encoded into the boundary conditions of the manifold you obtain after removing this region. So for instance, if we're interested in point-like particles in 2D, there will be some kind of disk-like region around it for which the energy is higher than that of the ground state. We remove it, so we are left with some open boundary conditions that we want to classify. And to do that, we begin by noticing that we can always freely glue a cylinder on top of this puncture, and this does not affect the topology. We can just absorb the cylinder in a way. This topological statement then gets translated into an algebraic statement, namely that the ground state subspace on the punctured surface defines a module over some algebra. And the algebra, which is often refers to as the tube algebra, is essentially the algebraic analog of another topological operation, which is that the gluing of 2 cylinders is diffeomorphic to another cylinder. And at the end of the day, we find the elementary point-like excitations as the simple modules over this algebra. So more concretely, although I don't want to go into the technical details, this algebra can be written conveniently as some so-called groupoid algebra, where so G here is the input group and alpha is some input cohomology class. But this algebra is isomorphic to a possibly more familiar one, that is the twisted Drinfeld double. The excitations are then organized into a category, which is the category of modules over this algebra, essentially the representations if you want. And it satisfies a well-known equivalence. Indeed, this category is equivalent to it's called Drinfeld center of another category. And this latter category can be thought as the input of the model. So as I briefly mentioned earlier, these models can be thought as Hamiltonian realization of the digraph return theory. And so now I want to establish essentially the dictionary between this Hamiltonian picture and the state sum picture. And this will be important for what I explain next. So generally speaking, if you have some n-dimensional extended TQFT, what it is, roughly, it's a theory that computes topological invariance. And these invariants, they have, I would say, various degrees of abstractness. So for instance, to a closed n-dimensional manifold, the partition function simply assigns a number. If this manifold has a boundary, to this boundary, it's going to assign a vector space. If this boundary has itself a boundary, then it's going to assign a category and then higher categories and so on and so forth. So concretely for the in 2+1D for our gate models, and I will start with the last item, to the circle, which is a one-dimensional manifold, the theory assigns to a category, which is precisely the category that encodes the point-like excitations. Now to the two torus, it assigns a vector space, which is just the ground state subspace of the Hamiltonian, and it can be conveniently written as the center of the tube algebra. Okay, and then to the three torus, these are well-known things. The number is simply the dimension of the previous vector space, which physically is the ground state degeneracy on the torus. Now, something that is interesting is that there are some relations between these quantum invariants. So the first one is obvious. I briefly mentioned it, that the dimension of the vector space assigned to the torus is equal to the number assigned to the three torus. But there is another one, analogous, that is possibly less familiar. There is a notion of dimension of a category as well. And when you compute the dimension of the category assigned to the circle, you find precisely the vector space that is assigned to the torus. And these relations, we refer to them as crossing with the circle conditions. And they are expected to hold more generally for fully extended TQFTs. And so what they are relations that relate the quantum invariant associated with a manifold to the quantum invariant associated with this manifold crossed with the circle. Okay, so now let's go to 3D and let me discuss briefly the loop-like excitations. So first of all, I want to clarify that here, by loop-like excitation, I'm not referring to at this point to fluxes or charges. I'm only referring to the topology of the defect, which will then support some fluxes and charges. So I have a string-like defect, and there is some regular neighborhood around it, which is a solid torus for which the energy is higher than that of the ground state. And then I proceed exactly as in 2D. I remove the solid torus, I'm left with a torus boundary condition, and I can classify these boundary conditions as the simple modules over some tube algebra. The only difference is now that the tube looks like this. It's essentially the torus cross an interval, so some kind of three-dimensional cylinder, if you want. Algebraically, it looks very much like the 2+1D scenario. It's just that everything is adapted accordingly. We have a sort of new tube algebra. The loop-like excitations are still encoded into a one category, which is the category of modules over the tube algebra. And there is an equivalence that is analogous to the one we have in 2 dimensions. So let me clarify something else, is that this category we found, what it encodes the most general type of loop-like excitations. So what are these loop-like excitations? They correspond to loop-like fluxes to which charges are attached while being threaded by another flux. And this threading flux is important because it can constrain the quantum numbers associated with the other flux and the other charge, and the charge. With this in mind, so the braided structure of your category encodes what is sometimes referred to as the three-loop braiding statistics, which is the braiding of two loops while being threaded by the same flux. Okay, so now let's talk about the string-like excitations. And again, by string-like, I'm not referring to a Wilson line or something like this. I'm referring to a topology of the defect, which will then support some flux and charge. So the study of the string-like excitation is quite more subtle than the loop case. So for the sake of time, I'm going to have to be slightly vague. But the idea is still in the same spirit as before. So we begin by looking at the regular neighborhood of the string, which we remove, and then we essentially want to classify the boundary conditions. Now we can proceed as before by considering a tube algebra. Now the thing is that the tube looks a little bit different now because the cylinder is an open manifold, and so we cannot quite take the tube as we usually do. In the sense that it's a bit pinched where the circle components are identified. But so adding this, we basically add the cylinder around the other one, and then it can be absorbed, and we can define an algebra in the same way. And we can look at the modules over this algebra, and we find a category, which is some category of graded vector spaces. Now, it turns out that this is not really the end of the story. Roughly speaking, the idea is that this process sort of only classifies the boundary conditions along the cylinder, but it doesn't really deal with the endpoints, right, along the circle components. We need to look at another gluing process for that, which is this gluing process where you sort of concatenate these tubes, and then it's equivalent to a longer tube. Now, the subtlety is not to these tubes. We don't associate algebra elements anymore. We already said that to the tube we assign a category, right? Which means that this process does not correspond to some multiplication in some algebra. What it actually encodes is a monoidal structure in our category. But this is fine. We can still proceed as before, trying to find the simple modules of this sort of categorified tube algebra. And in that case, these are modules over a category. And so putting everything together, all this is encoded into some higher category of the modules over this categorified tube algebra. And interestingly, we still have some kind of, we still have an equivalence relation analogous to what happened before. It's now with respect to some higher categorical center. Let me maybe clarify a little bit the physics and explain exactly what this sort of higher category we found encodes. So claim that it encodes the most general kind of string-like excitations, but let me now elucidate how it does that. So the objects of these categories or two categories correspond to boundary conditions for a string-like excitation. And so the kind of data that is there is like there is some extrinsic defect data, but there is also, it also specifies the possible fluxes that a string ending at this point can have. So there is some flux data as well. The one-morphisms then correspond to some diagonal quantum numbers for a string that sort of connects two endpoints, right, obviously. So there is some charge component in there. And then, well, let's not worry too much about the two morphisms. So let me now go back to the state sum picture. So now the model in 3D it's still a Hamilton realization of digraph-within theory. It's just it's a 4D TQFT now, which means that this theory is going to assign a category to two-dimensional manifolds now. So let me start with this layer actually. So the third item. And the category that is assigned to the two torus is precisely the category of the loop-like excitations that we derived before. Now, the upper layers can be obtained in a way analogous to the two-dimensional case, especially with sort of the notation I'm using. You can sort of intuit what's going to be the quantum invariance associated to the 3 and 4 torus, so that's easy. And the novelty is the last item. And this is the quantum invariant associated to the circle. So we know it's going to have to be some higher category. And the previous story that I sketched should motivate the fact that, but of course it can be made more precise, the fact that this higher category assigned to the circle is precisely this bicategory that encodes string-like excitations. So with all these preliminaries, I can now tell you about the main result, which has to do with this crossing with the circle conditions. So remember that these are conditions that relate the quantum invariant associated with the manifold, the quantum invariant associated to the manifold after crossing with the circle. So the first one is obvious, and it just says that the dimension of the vector space assigned to the 3 torus is the number associated to the 4 torus. Okay. The second one is analogous to what we had in 2D, which is that the dimension of the category assigned to the torus gives us the vector space assigned to the 3 torus. So it's all nice. But the last one is really the interesting one.
You're right about out of time.
Yeah,
so if you can just take another minute or two.
So the last crossing with the circle condition is the interesting one. There is also a notion of dimension for a higher category, and so which we computed. And maybe as expected, what we find is precisely the category assigned to the two torus. Now remember that this latter category is the one encoding the loop-like excitations, while the higher category is the one encoding the string excitations. So this condition gives us a clear relation between the mathematical structures associated with string and loop-like excitations. And as the name dimension suggests, there is this idea of tracing, which then you can be used to intuit in which way closing a string excitations gives you a loop excitation. As a matter of fact, this can be made very precise, and when you go through the computation, you really see how the loop-like excitations are obtained by identifying the endpoints of two string excitations. So that's the main result I wanted to tell you about, and I'll just briefly show this summarizing table. Thank you very much.
All right, thank you very much for an excellent talk. So now let's move on to our next speaker.